It is a time of two staples, two heroes of the Lean community. The first one is Riccardo Brasca from Paris Cité Université, who will tell us about number theory in Lean. Thank you very much, Riccardo.
Thank you very much for the invitation and the introduction. So sorry for the usual quirks with the video projector. Maybe one day we will have a verified in Lean video projector or something like that that always work. We'll see. Anyway, so the goal of my talk today is to try to explain a little bit what can be done in number theory using Mathlib, and I mean what can be already been done today, and what can be done in maybe with not too much work. And so it's a talk oriented for mathematicians, but you can listen to it even if you don't, if you are not a mathematician. You don't need to understand all the mathematical details. I will try to say something interesting for everybody, hopefully. Okay, so we will focus on algebraic number theory, just because this is the part that I know better of the library. There is also, of course, analytic number theory. And in my opinion, the library is a little bit more developed in algebraic number theory, but hopefully in a couple of months, we will also have a good library in analytic number theory. Okay, so let's start with something serious. So one of the main objects of study in number theory are number fields. So the first question is, how do we declare a number field in Mathlib? And you see, it's this line where I write variable k type star. So this means let k be a set, is the Lean way of saying let k be a set. And now I also want to say that it's a field. So I write field k. And at the moment, you can ignore the fact that I use a square bracket. Just say, so this part of the line means let k be a field. So technically, what I'm saying is let k be a set endowed with the structure of a field. So you see, remember that types are more or less sets in a first approximation. So k colon type star, forget about the star, means let k be a set. And now I also say endowed with the structure of a field. Okay? So after this line, in all this file, there is a letter k that is a field. Okay? So you can freely say let a and b be in k, and you can add a and b, multiply a and b. You can also divide a by b. Okay? Of course, I also want to be that our k is a number field. So I also add number field k. So after this line, k is a number field. So if you don't know what a number field is, it's not very important. It's a field that is a finite extension of Q. So it's a vector space over Q of finite dimension. But again, the definition, I mean, at some point it will be important, but you can understand something even without knowing the definition of a number field. Okay? So you can, if you are curious to see what is the definition of a number field in Mathlib, you can print the definition. You can actually print any definition in Mathlib, I mean in Lean. So let's see what a number field is for Mathlib. So you see, it's not very readable, unfortunately, because there are a lot of details, but the important part are characteristic 0 and finite dimensional. So essentially, number field K means that it's a field of characteristic 0. And so in particular, it is an extension of Q, and it is finite dimensional as a Q vector space. Yes?
Why do I have to declare K to be a field and then?
Okay, so this is a design choice. Actually, I mean, you can also do the other way around, but actually the number field K is the name is not 100% correct. It should be is number field. So number field is a property of a field. So we are usually pretty strict in Mathlib with names. Here is an example where we just decide to write number field, but technically it is a property of a field. So there are fields that are number fields and fields that are not number fields. So this name should be is number field. And maybe at some point someone will change the name. But this is just a name. And why we decided to have a property rather than package all the definition together? This is probably a design choice. I mean, it's an historic decision. Probably the reason is that very often you already have a field, and maybe in the middle of the proof you want to say, okay, now I prove that this field is a number field, but you don't want to define addition and division because you already have the operations. So it's probably more convenient to already having a field and saying, okay, this field is a number field. Okay. So let's, for example, so it's a finite, it's a characteristic zero field. So in particular, it is an algebra over Q. And the way we can check this in Lean using the command synth. So this line essentially means, Lean, are you able to find a structure of a Q algebra over K? And you see that Lean answer with the, I mean, this is the name of the declaration. It doesn't matter, but there are no errors. So you can do the same, for example, asking, do you know that the integers are a ring? And you can just write synth ring Z, and Lean will say, yes, I know that the integers are a ring. But if you ask, Lean, do you know that the integers are a group? Sorry, group maybe is a, do you know that the integers are a field? Lean will say, no, I don't find this definition. So I don't think the integers are a field. Okay, now a slightly more advanced observation is that maybe in your mind, algebra QK is the same, I mean, and not only in your mind, but you think that algebra QK is exactly the same as the fact that K is of characteristic zero. This is, of course, mathematically correct, but my suggestion is if you want to do number theory, just assume always characteristic zero. Don't never write algebra QK. This is, for example, proving this lemma, the fact that if you take a field that is a finite, an algebra over Q and a finite extension of Q is unfortunately a little bit annoying. By annoying, I mean, it's not, it's one line because it's essentially already in Mathlib, but the point is that this is not automatically found by Mathlib. And for a technical reason that we don't know how to solve, essentially. But so my suggestion is just forget about algebra QL, just use characteristic 0L if you want. Okay, so now something that is probably interesting for everybody, how do we play with fields? So forget about number fields for 5 minutes. So remember that yesterday we saw the ring tactic, so that it's very useful to prove algebraic identities like the following one. So for example, if you want to prove that the sum of x plus y, the square of x plus y, it is what it is, well, ring is able to do it automatically. And I really invite you to try at least once in your life to prove this lemma by hand, using only associativity, commutativity, and so on, just to see how painful it is. Just once. It's probably a good learning experience. And if you try to do the same with the cube, you just realize that, okay, it's doable, but it's super annoying. I cannot spend my life doing stupid computations like that. So it's very good that ring exists. And the ring is really, really good. When every time you have a computation, an algebraic manipulation like that, it always works. In practice, it always works. So that's very good. The only problem with the ring is that it's not so smart if you also want to divide. So for example, if I want to prove this, is it big enough? Yes. Is it big enough for everybody? Okay. So if you want to prove, we want to prove this very interesting lemma that we take x in k different from 0, and then x divided by x is equal to 1. So not very deep result. But you will see that ring. Let me say that these slides are already in the Italian repo, so you can follow them live if you want, and you can play with my examples live if you want. So if you try ring, you will see that ring doesn't work. Essentially, because ring is not meant to be used with divisions. So if you have divisions, ring will probably not close your goal. Maybe yes, but usually no. There is a deep reason why division is more complicated than multiplication, but in practice, what you can try is the field simp tactic. So field simp is a little bit like ring in fields, and what it does, it erases denominators more or less, and sometimes is able to automatically close your goal. So for example, in this case where you have x divided by x, you can just write field simp, and you see that Lean is happy, you finish the proof. Okay? Of course, this result this literal result is in Mathlib somewhere, but you don't need to guess the name or to look for it. Just use these tactics that are very, very nice. So in fields, we can divide, of course, but we can also consider the inverse, that is this z minus 1. So you remember that if you want to see how to write these Unicode symbols, you can just hover with the mouse, and you see that you can write the -1 just with \-1. So you can divide by z or multiply by the inverse. Of course, these are the same thing. And now, if you want to prove this equality, that again is a stupid algebraic equality, well, we can try field simp. And you see that field simp this time is not able to close the goal, but it leaves us with a much simpler goal. In particular, all the denominators are gone. And now the new goal is x plus y equal to y plus x. Okay, this is a very easy algebraic identity that ring is supposed to be able to solve, because now there are no divisions anymore. And actually, ring close the goal. Okay, so field simp is really like that. You write field simp, sometimes it works and you're happy, but often it just leaves a sub goal that ring is able to do. Okay, so this is, if you want to, this is useful. I mean, I'm presenting this with number fields, but if you want to do computation with real numbers, this is the same thing. I mean, the real numbers are a field, and Lin knows it, so you can use field simp with the real numbers. Okay, something else I would like to say is that maybe sometimes you want to try to guess the name of the lemma you want to use, and I don't want to explain the naming convention of Mathlib, but let me just say that here, so this lemma should be the fact that x divided by y times y is equal to x if y is different from 0. It should more or less be in Mathlib, and it's probably called div mul cancel, because you divide and multiply, and these two operations cancel. But of course, you are not in a group, because the field is not a multiplicative group, but it is almost a multiplicative group. And so all these lemma have a little zero at the end. So just this, the little zero at the end means, okay, probably you are working in a group in an algebraic structure such that the subset of elements different from 0 are a group, and you know that the element you are interested in is different from 0. Okay. Okay, and let me also say that grind is able to play with division. For example, if now we take x and y in K, and we assume that, you see, the assumption H is basically that x plus y cube is different from 0. But I just manipulated it a little bit, so I expanded the cube, and I added x times y squared on both sides. But this is literally x plus y square cube different from 0. So x plus y different from 0. But you have to realize that. And now you can divide x squared minus y squared by x plus y, and the result is x minus y. And you see that green is able to do it by itself. So here green is pretty smart, because is able to understand that this h means that x plus y is different from 0. So grind is also a nice tactic to use with divisions. So unfortunately, divisions is just harder than multiplication. So for multiplication and addition, just use ring. And if you also have to divide, well, sometimes you have to try various tactics. And if grind works, fine. If field simp works, fine. But sometimes you have to play a little bit with it. And of course, you can always try to send all these lemma to Aristotle. I guess he's able to prove them like in 5 seconds. I mean, I hope so. Okay, now let's move to something a little bit more interesting. So the ring of integers of a number field. So mathematically, the ring of integers of a number field is a subset of. So the ring of integers of K is the subset of K given by elements that are roots of a monic polynomial with integer coefficients. Again, you don't need to understand what this means or why it is an interesting object. Just know that mathematically, when you start with the number field K, you have an interesting subset of K. And it happens that this subset is also a subring. So let's just say that it's the subset given by nice elements in some sense. Okay? So in Mathlib, you can just write OK to have access to this ring of integers. You have to open number field to activate this notation. Then this is the usual notation that you find in a paper in number theory. And you see that Lin knows that the ring of integers is actually a commutative ring. So if I ask Lin, do you know that OK is a commutative ring? Lin says yes, I know it. Okay, so now there is an interesting thing that I think it's really interesting for everybody. So remember, this OK is mathematically, it is the subset of K given by elements that are nice in some sense. So mathematically, it is a subset of K. There is nothing else to say. But well, in Lin's type theory, OK is a new type. So it's not a subset of K. It's really a separate type. So remember that everything in Lin, so everything is every term, so everything you can write has its own type. And if I say that X is of type OK, so mathematically what I'm saying here is let X be an element of the ring of integer. So the type of X is OK. The type of X is not K. So technically, elements of OK are not element of K. And so if I take an element X of OK and an element Y of K, how can if I am 100% precise, I cannot add X plus Y. Why? Because which addition I'm talking about? Well, it's of course not the addition of OK, because Y is not in OK, but it's not even the addition of K, because, well, now X has type OK. So if I want to be 100% precise, I cannot add X and Y. This is, of course, if you want to do mathematics, is ridiculous, because in your mind, OK is a subset of K, so you should be able to add X and Y. And luckily enough, if you write X plus Y, you see that Lin doesn't complain. So somehow he's able to add X and Y. But if you look closely, you see that he's not really adding X plus Y, but he's adding this arrow X. So what Lin is doing here is that he's inserting what is called a coercion. So in practice, it means that there is a canonical map from OK to K that mathematically it's the inclusion. So it's a map that you never write. Lin writes it for you. So the bad news is that there is this small difference with usual mathematics, but the good news is that 99% of the time, Lin does it for you and you can ignore this difference. So you see that you just write X plus Y and Lin does something for you that you don't care about, but you can essentially ignore this issue. Just know that sometimes there are these errors that appear, and this is just because Lin has to do something before adding X and Y. But again, you can essentially ignore all this issue. So 99% of the time you can ignore them, but sometimes, unfortunately, Lin asks you to prove something about these coercions. This is unfortunate, but we have tactics to do that. For example, imagine that you want to prove that if now you have A and B in OK, and you want to prove that if you add A and B, now this is the addition in OK, and you see this element as an element of K, is the same as viewing A as an element of K and adding B as an element of K. So again, mathematically, there is nothing to prove because this arrow is the inclusion, so it is essentially the identity. This lemma is very easy, but sometimes it can be a little bit annoying. And my suggestion is just to use the normcast tactic that essentially try to get rid of all these arrows. So if you have a goal that involves this arrow and is a goal that mathematically is empty, so that there is no mathematical content, just write normcast and see if it works. Okay? As usual, you can hover with the mouse and you see that it is \MCO. MC is the mathcal is from mathcal the LaTeX command. But yeah, in this since writing mathcal O is long, we just write MCO. But pay attention that usually in normal mathematics K is a subscript. Here there are no underscores, so you just write O space K, and you have to use this open number field line to activate this notation. Okay, another small example. Now we take A in OK. We suppose that A is different from 0, and we want to prove that A multiplied by the inverse of A is equal to 1. Of course, we cannot take the inverse of A in OK because OK is not a field, so we take the inverse of A as an element of K. Again, this is a stupid lemma. It should be in Mathlib. And what you can try in this line, if you write exact question mark, so you ask Lin, well, do you already know exactly this result? you are a little bit disappointed because you discover that this result is not in Mathlib. And you can say, okay, these Mathlib guys are not, I mean, they're not doing their job, but and Lin says, you can try apply question mark that gives you the goal, but leaving you a smaller goal. And if you try apply question mark, it finds this lemma, mul inv cancel 0, and you see that the new goal is that A is different from 0. And now you can complain, well, I know that A is different from 0. Well, but if you really pay attention, you see that the new goal is upper arrow A different from 0. So the point is that now you need to, of course, you are dividing by A inside K. So what you need to know is that A as an element of K is different from 0. And again, mathematically, this is exactly HA. So there must be a lemma somewhere saying that A is different from 0, if and only if A as an element of K is different from 0, but you probably don't want to find this lemma, and you can use the exact modcast tactic. So you see, the goal is very close to your assumption HA. The only difference is this coercion, so this arrow, and exact modcast try to solve this problem for you. So if you just write exact HA, it doesn't work because HA is not literally your goal, but it's very close to your goal. So exact modcast is a smarter version of exact that get rid of this annoying coercion. And I mean, this is I did this with the ring of integers of a number fields, but it happens every time mathematically you have a subset, and very often in Lean, this subset is actually a new type, and you have the same problem. So if you you don't need to understand all the details. Sometimes you can just ignore this difference, but sometimes you are faced with these problems, and I think it's interesting to have a little bit of an idea of what's going on. Okay, so now let's move on to the units. So in number theory, another very important object are the units of a number field, so the invertible element of this ring. And in Lean, if you have any ring, actually any monoid, you can just write exponent x to have access to the unit. So if you write OK star, I mean, technically it is an x, but it really looks like a star. This is the subgroup of unit of OK. And you see that Lean knows that this is a group. Okay? And now you have exactly the same problem as before, meaning that this is technically not a subset of OK, it's a new type. And it's exactly as before. There is a coercion from the units to OK. Okay? And there is also a predicate. So there are two things you can do about the units. You can say that you can start with actually a unit, so an element of this new type, or you can say that an element of the ring of integers is a unit. And so we have this predicate is unit, and you can more or less move between these two notions if you want. So for example, if you have a unit, you know that the associated element is a unit. So you see, is unit U is a predicate, so is a mathematical statement that is sometimes true, sometimes false. It depends on U. I mean, no, it's a statement. So you have U, an element of the ring of integers, and you can say this element is a unit. Sometimes it's true, sometimes it's false. It depends on you. Okay? But if you have V that is a unit, so is an element of this new type, well, the associated element is of course a unit, and this is called V dot is unit. It's full of this. Again, at the beginning, this looks like completely craziness and very hard to move between these two notions, but actually you have just to get used to it. It's not very difficult. So you see that now you have two. So if you want to move from the units to K, so mathematically the units are a subset of OK that is a subset of K. So the units are a subset of K. But now in Lean you have two coercions. And sometimes the fact that you have these two coercions is a little bit annoying. For example, this lemma is not difficult, but it's a little bit annoying to prove because you see that now you have two arrows because you go from units to OK and to OK to K. You can try to prove it. It's not that difficult. There is a proof in one line, so at the end of the day it's okay. But it can be a little bit annoying. And again, is a lemma that is mathematically is completely trivial. So it's just a very easy computation. Okay. Okay, so let's move on to something more interesting in number theory. So this is also related to the project I proposed yesterday, so the computation of the ring of integers. And you may, so this is a little bit more for mathematicians. So we have the trace and the norm function, the usual ones in number theory. So these are functions from k to q. So if you take an element of k, its norm, for example, is a rational number. And mathematically, the property is that if you start with an element in OK, then the norm is an integer. And I would like to explain how do we say that in Lean. So the point is that you cannot. So when you take, if you start with x in k and you compute the norm, well, this norm will have type q, because the norm is a function from k to q. And you can, saying that this element is in Z is a little bit annoying, because Z is not a subset of Q. There is the same problem. Z and Q are of course related, but it's not true that one is included into the other. So, and even more annoying, the point is that Z is not the ring of integer of Q. Well, I mean, in which sense it's not? Well, the fact that Z equals OQ is a statement that you don't want to consider in Lean. It's probably it's surely undecidable in Lean, but the point is that, of course, these two rings are isomorphic. So in some sense, mathematically, they are the same thing, but one is, so you see, Z is constructed in some way in Lean, and now, and much later in the theory, we defined what is the ring of integer of a number field. And of course, these two constructions are very, very different. So there is no hope that the ring of integers of Q are literally Z. There will be isomorphic, of course. And this is also a common problem when you do essentially any mathematics in Lean. Very often, you don't want to work with a specific object. What you want to do is to find what we call the characteristic predicate of this object. So what we want to do is to work with any ring that is abstractly the ring of integers. So that abstractly it is isomorphic to the ring of integer. And for example, if you know what the AKLB setup is in number theory, so usually you fix two Dedekind domains and you take a finite extension of the ring, you fix a Dedekind domain and you take a finite extension of the fraction field and blah, blah, blah. And you get these four objects, A, K, L, and B, where A and B are in, A is included in K and B is included in L, and actually K is the fraction field of A. And so my point is that you see, this is the way we write this in Lean. And again, you don't need to understand all the details, but you see that it's never written. So A, for example, let's have a look at A and K. So the main example is when A is Z and K is Q. So this is the main example. And you see that I never wrote that A is, I mean, K is not the fraction field of A. Is a field that it is abstractly the fraction field of A. So here I'm saying that I start with any field that is isomorphic to the fraction field of A. And this is very convenient because, in particular, Q will satisfy this property. So I can apply this theorem to Q. But maybe at some point, for some reason, my K is Q of X modulo X. That, of course, mathematically, this is Q. But for Lean, this is not equal to Q. It's isomorphic to Q. It's like if you do analysis, I don't know, you have R to the N, and at some point, you have that N is equal to 1. Well, this is not equal to R. It's R to 1. Of course, it's very close to be R, but technically it's not equal to R. It's isomorphic to R. And so you want to state all your theorem for any object that is isomorphic to R or isomorphic to Q in this situation. And this is very important. If you don't do that, at some point you realize that in your theorem you have like chains of 4 isomorphisms and your theorem is unreadable, and working with your statements is essentially a huge pain. So this can look, maybe for you it looks a little bit crazy, but you just have to do this from the beginning, and then everything is pretty nice. Okay. Okay, so I'm of course late, so I started at 5 past. Okay, so let's move a little bit faster. So let's see some serious number theory that is in Mathlib. So of course, Mathlib knows a lot of things about ideas of the ring of integers. For example, we have the extension of the norm to ideals. So we can compute the norm of an ideal that, of course, it's another ideal. But let's really see some more advanced theorem that is in Mathlib. So for example, the basic property of the ring of integers is that the ring of integers is a Dedekind domain. And okay, this is in Mathlib. So is Dedekind domain, you see, this is a property of a commutative ring. There are commutative rings that are Dedekind domains and commutative rings that are not. And this is why the property is called is Dedekind domain. It's exactly like number fields. The problem is that number field is not called is number field, but it should be. And if I ask Lynn, do you know that OK is a Dedekind domain? Lynn says, yes, I know it. Okay. And so in particular, this means that somewhere in some sense, Mathlib knows the unique factorization of ideals in a ring of integers of number fields. And this is again something quite interesting too. So if you look at the theorem, you see that the theorem that ideals in a ring of integers of number fields have unique factorization into product of prime ideals, it's never written. It's written nowhere. So you can start complaining, well, so this is essentially useless. The point is that the way this is stated in Mathlib is a little bit tricky. So first of all, in Mathlib, we realized that the set of ideals of actually any ring, so if you have two ideals, you can multiply the ideals, you can add the ideals, you have the zero ideal, you have a neutral element for multiplication. So you see, the set of ideals, it's almost a ring itself. The only thing is missing is that you cannot subtract ideals. Well, the algebraic structure that is like rings but without subtraction is called semi-ring. And Lynn knows that the set of ideal is a commutative semi-ring. Again, you can say, okay, this is just terminology. But the point is that now, if you have a theorem about a commutative semi-ring, well, you can apply it to ideals. For example, a ring, the tactic ring, that also works for semi-ring, is able to prove that if you have two ideals I and j, then I plus j squared is equal to what it is. Because this is just a computation in a commutative semi-ring. So ring will do it. Ring will know, that doesn't know anything about ideals, but this set is a commutative semi-ring. So ring is able to do computation in that. Well, so you see, here I computed the cube of I plus j, and you see it's done by ring. So ring, I mean, the name is ring, but it also works in semi-ring. And now Mathlib has a notion of being a unique factorization domain that works for any semi-ring. It actually works for any monoid. So the actual name is unique factorization monoid. And you see that Lynn knows that the set of ideals of a Dedekind domain is a unique factorization monoid. So if you want to find the theorem that there is a unique factorization into product of prime ideals, you just have to apply the general theorem saying, well, in a unique factorization monoid, elements can be factorized in product of prime elements. This theorem is true by definition. The mathematics is hidden in the part that the ideals of a Dedekind domain are a unique factorization monoid. So you see my point. This theorem is not written explicitly for ideals in a Dedekind domain. It's just written for any unique factorization domain, and then somewhere in the library it is proved that the ideals form a unique factorization domain. So if you want to play with ideas, you have to have a look at the general theorems about unique factorization domains that are actually called unique factorization monoid. Okay. Now let me just show off a little bit of what we are able to do in Mathlib, just to show you that we are able to do some serious number theory. So for essentially the point is that we know all the basic graduate level algebraic number theory. So for example, here is a statement of the Dedekind-Kummer theorem. So how a prime ideal factorizes in, so you start with P, a rational prime, and you look at the factorization in OK, that the factorization has the same shape as the factorization of the minimal polynomial modulo P. I mean, if you know what the theorem says, you know it. And much more interesting, the finiteness of the class group. So this has been added by Filippo and his collaborators 4 years ago. 4 years ago. So Mathlib knows that the class group of a ring of a number field is a finite set. This is an absolutely non-trivial theorem. So something that, I mean, there are actually no, it's a really non-trivial theorem. Now we also have maybe since 1 year or two the Minkowski bound. So the fact that any class in the class group contains an ideal of norm less or equal to the Minkowski bound. And now from maybe 1 year, we know all the basic results about ramification and inertia degree. So this is the standard formula. The sum of the ramification multiplied by the inertia degree is equal to the degree of the extension. And from a couple of months, we also have Dirichlet unit theorem. So we know the rank of the unit group of a ring of integers, and we have results like the Hermite-Minkowski theorem. So we know that if you take a non-trivial finite extension of Q, then the discriminant is at least 2. And funnily enough, I think that we are still missing the connection between the discriminant and the ramification. That shouldn't be hard. So I don't know why it's not there. Maybe just because no one worked on it. So it's there.
The co-different to the ramification is there.
Yeah, but for example, how is the fact that spec Q is simply connected? So do we have it?
Spec Q.
Yeah, I mean, the fact that every non-trivial extension is ramifies somewhere.
It's an open PR.
Okay. So we almost have it, but I mean, the math is here. So once we have this mathematically, there is nothing less to do. Okay, and I mean, and we also have a Hermite theorem. So okay, so these last theorems were just to show you that what can be done today, and so I don't have time to show you other part of the library, but I would just like to let you know that we have elliptic curves in Mathlib over any field. So we have a proof that the rational points are a group. We have a little bit of the theory of elliptic curves. For example, divisions polynomial are there. We have a not so basic theory of modular forms. This is still quite new, so we don't have a lot of results. But I hope that in a couple, maybe not this year, but in a couple of months, we will have a finite dimensionality of the space of modular forms. That is the first non-trivial results in the theory. And of course, as everybody knows, Kevin is working on Fermat's theorem, so he needs a lot of results about modular forms. Even if the modular form used by Kevin are not the standard modular forms, are a different version. So, but anyway, he needs a lot of results of this kind. Okay, so maybe your last question is how you can. So how are there something that you can do in a reasonable amount of time? So, in my opinion, a very good way of learning the library is just to take your favorite number theory object, for example, your favorite number field, and try to compute explicitly some invariant. So the project I proposed yesterday is exactly this one. So it's maybe the really most basic example. Take a quadratic field and compute the ring of integer. But you can also compute the discriminant if you want. You can try to compute the units. I mean, stuff like that. Okay. And if you are interested in such a project, let me say that Chris Burbeck recently launched a project called the Lean Bridge, where their goal is to formalize a lot of computation done in the L function and modular form database. So this is an internet database where there are a lot of explicit computation about number fields and also modular forms, but let's stick to number field for the moment. So the goal of Chris project is to formalize a lot of results in this database. Maybe try to automatize the formalization in some sense. And if you are interested to more theoretical aspect, well, I would really like to have the theory of a real cyclotomic extension in Mathlib. So we already have cyclotomic fields in Mathlib with an extensive library. but we don't have anything about the maximal real subfield. And actually, my goal is to so in the project that we finished 2 years ago, we proved the Fermat's theorem for regular primes. So this is not in Mathlib, but it is in a separate repo. So now we know that if P is a regular prime, whatever it means, Fermat's theorem holds for P. But in practice, it's quite difficult to show that a given P is regular. So I have a proof of this for P up to 13, I think. But for example, the first non-regular prime is 37. But proving that 23 is regular is really annoying. And it follows from this computation about the real subfield. And so if we are able to prove this, then we have an actual proof of Fermat's theorem for all n smaller than 37. Actually, a lot of other exponents, but in particular for all n smaller than 37. And let me also stress that this would be a completely sorry-free proof. That is not what Buzzard is working on. So if in 3 years, for 4 years, when Kevin will have finished his project, still the proof of Fermat's theorem will not be sorry-free, because Kevin is assuming a lot of stuff from the 20th century number theory that they are not proving. So it would be nice to have a lot of examples. And just to finish, let me say that with Filippo we have some money for a PhD position next year. So if you or some of your students are interested to work in formalization of arithmetic, just contact us and feel free to ask us questions. Okay, and I'll stop here.
Okay, maybe we have time, like a couple of minutes for questions. All right. Yes. Can you wait for the microphone? Can you wait for the microphone, please?
So what is the smallest prime that we cannot prove that it's regular?
You mean in Lean?
Lean, yeah, I mean.
Is 17.
17.
I mean, I technically, I have a proof that works for 17, but it's, I mean, I can write a proof, but the point is that you can do it with an explicit computation. And so I use Sage to give me all the data, and the proof for 13 is already quite slow to compile. I can write down the proof for 17 and just stare at my computer for probably 10 minutes. And I'm sure that at the end it will say that's okay. And technically I can even do the same for 19, but I'm pretty sure that my computer would explode. For 19, it's really like you have to test like 1,000 small primes. So 17 and 19, the problem is just that I don't have enough brute force.
I mean, one could prove this condition with Bernoulli
No,
numbers.
but then there are mathematical difficulties after 19. So up to 19, mathematically the proof is the same, and then it's really deep, because regular means that the P does not divide the order of the class group, and up to 19 the class group, the order of the class group is 1. So but with 20, this is why I say that 23 is really difficult, because the class group has order 3. And here, even with Sage is not able to prove that. I mean, maybe nowadays yes, but it's not so easy to prove that 23 is a regular prime. I mean, there is a theorem, a difficult theorem that trivializes the question, but you have to prove the theorem.
Any more questions?